Hello everyone. Let's start talking about another type of device, which is the P-channel MOSFET, also called PMOS. So this is very similar to the NMOS device, but you will see that some of the voltages, currents, and so on are measured in the opposite way, and the channel is P-channel in this case, not N-channel. So you'll see it as we go along. So the structure of the P-channel MOSFET looks like this, and as you can see, it's very similar to the N-channel MOSFET, except that the drain and the source diffusion regions have P plus material connecting to an N substrate. So in the NMOS device, we had a P substrate. And of course, we also have a bulk, which is typically not shown in our diagrams, but it is there. So that connection is made using an N plus region instead of a P plus region. So please go ahead and take a look at this, but also look for the similarities and differences between this and our presentation on the NMOS in the past presentations. So again, the structure is very similar. We have a gate, source, drain. We have an insulating layer, which is silicon dioxide, etc. So really not too much difference here to start with. And the simplified diagram, sort of a 2D diagram you could say, looks like this. Again, very similar. But on the schematic symbol, you will see that the source terminal has an arrow going in. On the N-channel device, the arrow goes out. The arrow points out of the device on the source terminal. And but everything else looks very similar. Typically, as I said, I'm repeating myself, but the bulk terminal is usually omitted. It's not typically shown because we typically deal with the gate drain source, as we did with the N-channel. So we know that in a MOSFET, the current flow is between the drain and the source terminals. And the way that happens is there's a channel formed between the drain and the source under the gate. Very similar to the N-channel. All right, so this is true for MOSFETs in general. And the amount of current flow between the source and the drain is controlled by the voltage that's applied to the gate. Right, so this is a true statement for any MOSFET, really. So it's still true in this case as well. Now, the drain and the source terminals are interchangeable, because in fact, if you look at them, they're symmetrical. There's nothing that distinguishes one versus the other one, except for the fact that on the schematic symbol, there's an arrow pointing into the flat horizontal line for the source. But besides that, they're really identical. However, in the case of the PMOS, the voltage that is higher, right, is assigned the source terminal. So if this whatever voltage is higher between the source and the drain, that terminal with the higher voltage, that's assigned to be the source terminal, and that's the terminal we typically draw the arrow with. And the current flows, in this case, from the source to the drain, right? So this is a little bit different because in the case of the N-channel, it flows from the drain to the source. So here it flows from the source to the drain. Since the source has a higher potential than the drain, so it's sitting at a higher point, the source to gate voltage, VSG, controls the amount of current. Now I should say that in some books, they'll still write VGS for a P device, but you have to remember that the numerical value of VGS is going to come out negative. So what I'm actually doing is I'm actually flipping the subscripts in such a way so that for the most part, we're going to still deal with positive numbers. So some books do it another way where they just will take VGS, but you have to remember that VGS is negative. So if we do it this way, then you'll have positive voltages for VSG. So VSG, the source to gate voltage, because the source is going to be higher than the gate, that voltage controls the current flow. So in other words, Once again, in the PMOS, this is a voltage control current source, with the controlling voltage being the source to gate voltage. Okay, so once the source to gate voltage is above a certain threshold, VTH, and I notice the magnitude because VTH, the threshold voltage for a PMOS, is given as a negative number because the gate is more negative than the source for a PMOS device. But in most of the calculations, if you use VTH with the magnitude and stick with the VSG, VSD, and so on with the polarity, the subscript changes, you should have really no problem. The equations will look very similar. But the point is that once we have some source to gate voltage above a threshold, a channel will be formed. So just like the N channel. Now, this channel contains free holes. Okay, in the N channel, it was free electrons. Okay, but in the case of a PMOS, the channel that forms is made up of holes, and hole movement is the result. Hole movement will result in the current flow, basically, right? So this is a P channel device, PMOS, and so the holes are the reason for the current flow. Now, if you want to take a look at sort of like a two-dimensional view of what's going on, here we have like a sort of a split view, side view of what's going on with the gate, source, and the drain. And to operate this the way it's supposed to operate, we have to apply voltages as shown. For example, the source to gate voltage has to be applied with the polarity as shown. Source has to be more positive than the gate by VSG volts. So gate has to be more negative than the source, depending on how you want to say it. And when you do that, of course, since the gate is more negative than the source, what happens is the positive ions, excuse me, positive ions are actually attracted to the region right below the gate. So there's a channel formed there, and if the gate voltage is made more negative than the source enough above a threshold, then you'll have these holes which are sitting right under the gate, and a channel is formed. Now this is a P channel as opposed to the N channel. We have free holes that allow the current flow between the source and the drain. Okay, but again, please note the polarities here. In a PMOS operation, the source has to be more positive than the gate. Furthermore, the source has to be more positive than the drain. Okay, this is opposite of what we had for the NMOS. In an NMOS, we have to have the drain more positive than the source and the gate more positive than the source. So those voltage sources that are drawn in blue, their polarities were with the plus on the right side. Okay? And so VDS was a positive number, and VDS was a positive number, and VGS was a positive number. So here the polarities are changed. Now, what I'm saying is I could still write VGS with the positive on the right and the negative on the left for the source right there. Okay. However, the value of the voltage source has to be negative then. Okay. So to avoid writing a negative value of the voltage source, I just flip the polarity, which shows really what's going on. Source is more positive than the gate, and source is more positive than the drain. So this is the typical way that you have to have the polarities for the voltage sources or voltages applied to this device for it to do something, right? For current flow to be achieved. But again, the holes are attracted to the drain terminal, okay, because they're positive, and the drain is more negative. So the positive is attracted to the negative, and this channel is formed, and there's electron flow from drain to the source, right? Electrons are flowing from drain to the source. Why? Because the source is more positive. So the electrons are going from the drain to the source. Therefore, the conventional current, right? We don't look at the electron current, we look at the conventional current, is that positive current is flowing from source to the drain. Okay? So the current flows the way we will write the current flow is that the current flow, the drain current or drain to source current or source to drain current, however you want to write it, that current in the channel is actually the positive current is flowing from source to the drain. Okay, some books will write ISD to notate it's going from IS, source to the drain. Some books will have IDS, but the value will be negative. Okay, or they'll just write ID and the value will be negative. But the fact of the matter is, positive current is flowing from source to the drain. Okay, so you have to kind of get a little bit of a understanding of that. All right, so let's move on. If you want to look at the structure, looks like this. Very similar, very similar to the N channel, but now we have an N substrate instead of P substrate, and drain and the source are really N plus regions. But we also have the width, the length, the oxide thickness. I mean, those are the same parameters, though those really haven't changed. What has changed is that because the channel is formed by holes, we have to talk about the hole mobility, which is mu sub P, right? When you write mu N Cox for N channel, we'll write mu P Cox for the P channel. And the hole mobility is 480 centimeters square per volt seconds. So this is lower than the mu N, which is something like 1350 or something. So holes are roughly 3 times slower than the electrons. Okay? But that's a property of the material. We really can't do anything about that. That's a given. We don't choose that. Okay? So if you're given a certain MOSFET technology, oxide thickness, gate capacitance, and per unit area, all that stuff is given. You can't really do anything. And then the I said electron mobility here. I should really say hole mobility. So this should be hole mobility. So since the hole mobility is constant, the parameter mu p Cox is typically given and expressed in microamp volt squared. So remember that we're typically using something like mu n Cox being about I think it was like 200 microamps per volt squared. Mu p will be similar, but if everything was the same, we would expect that to be a third of the mu n Cox. So because the mu p is about a third of mu n, but that'll be given, and whatever is given, we'll use. So that's the same. And then of course, device length, device width. Again, this is something that the designer has a control of. Threshold voltage. So the threshold voltage, as we know, is also a property of material. And for PMOS, VTH actually numerically, just VTH, is negative. But in a lot of the expressions, you'll see that we'll just take the magnitude, the absolute value of VTH, to set up the difference between, for example, gate source voltage and how much difference between the gate source voltage and the threshold. Because we want to know, once we have a high enough voltage for VGS, or VSG in this case, then we have a channel formed. So the difference between the source gate voltage and the threshold, that's a measure of what that difference in voltage is. And of course, if we apply a voltage that's less, no channel is formed, no current flows, and we're in cutoff as usual. So this is just some parameters. Most of them are going to be very similar. Only difference is, like I said, mu p is going to be a different number per se, but mu p Cox is given, so we don't have to worry about that. And VTH is going to be negative. So that's the major difference here. Other than that, the structure of the device looks pretty much the same. All right, so what else? Well, again, if you want to take a look at how typically the voltage polarities are going to be, what's more positive than what terminal is more positive, this would be pretty much what you look at. But again, when you do circuit analysis, this is not what we draw. We draw the actual the schematic diagram, the simplified schematic diagram. So on the left, you see that we've applied a VSG, right? Source has to be more positive than the gate, or gate has to be more negative than the source. Same thing. So we have that kind of a voltage source. And then VSD is applied source to drain because source has to be more positive than the drain. And current, the conventional current that we normally measure, is flowing from source to drain. Okay, so what I have on the left there on the bottom, it's the same as the picture up there, but with a schematic diagram. So current flows from source to drain. Notice that positive current is coming out of the drain terminal. Okay, now if you insist on measuring the current as current going into the drain terminal, in other words, like this way, okay, then your drain expressions, the equation for the drain current, will involve a negative sign out front. But if you want to avoid that, then you just have to realize that for PMOS, current flows out of the drain. Positive current flows out of the drain. So if you do that, then you're going to have to carry around that negative sign. That's what I typically do. Also, there's a convention in circuit analysis or schematic diagrams, and we've done this before, where current flows from top of the page to the bottom of the page. Also, more positive voltages are drawn on top of the page and more negative voltages are drawn on the bottom of the page. So if you want to draw the circuit diagram on the left by using that convention, which is typically where we do it, you end up with the circuit diagram on the right, which is just the circuit diagram on the left flipped upside down. Okay, you can see again the source terminal, the terminal with the arrow, is on top now. Okay, and the drain terminal is on the bottom, and the current is flowing out of the drain. And again, there's no gate current, so IS flowing into the source is equal to ID flowing out of the source. So the current is flowing source to drain, as we've said. Okay, so this is a point of confusion because usually, if you're used to the NMOS, the source terminal is on the bottom, drain is always on the top, okay? But remember, the source terminal is the terminal that's more positive in terms of PMOS, and therefore the arrow that's pointing into the device shows that that's the source terminal, that's the more positive terminal, and that's the terminal on top, if we want to do the conventional way. Okay, so this is just an introduction as to what the general structure is and what the general idea is for PMOS. So next time we'll look at more of the characteristics. In other words, the drain current characteristics. What are the drain currents in the triad region and the saturation region and how they look like? Now, for the most part, they're going to be the same, but the difference that you'll see is change of subscript, absolute value on VTH, and also the fact that the drain current flows out of the drain. So current is flowing from source to drain, not drain to source like the NMOS. So with that, I think I'm going to call this a day, at least for today. And I'll see you next time.